the present video is going to be dealing with the statics statics analysis issues with virtual parts, and the details of this particular presentation can be found in the proceedings of this conference, Material to Design in 2017. And let me first tell you what the story about this virtual parts is. Many years ago, let's say about 50 years ago, when NASRAM program, 60 years ago, NASRAM program was the primary finite element program in industry. They introduced this thing called rigid elements. In fact, there were 3 of them. There was RB, rigid bar, there was RB2, and there was RB3. The virtual part in Catia is a variation of those elements, and here's the way actually it is being used. So let's take the bar. Look, if you look at the screen on the very top, I have a bar which is 150 millimeters long. It's clamped at the left side, and at the right side there is a force acting, say 1,000 Newton. Now, let's assume that the 50 millimeters on the extreme right is made of a material that's a lot rigid, more rigid, bigger stiffness, bigger Young's modulus than the first 100 millimeter on the left side. Okay, it is possible, of course, it is possible to model this thing as a 3D, three-dimensional, 150 millimeter long, bar, and then which is made of basically 2 types of material. The left side is some Young's modulus. The right side, the 50 millimeter on the right side, has a much bigger Young's modulus, and then run the program. However, what happens is that because the 50 millimeter at the right side is much more rigid than the one on the left, then really not much stress is going to be developed in it, and it's going to basically move as a rigid body. Okay, so the whole concept of virtual part is not to model the extreme 50 millimeters on the right, but instead create what is called the virtual part. So there's no geometry associated with it. However, it's that diagram in the middle on the top left corner, and the red stuff is the virtual part, which the geometry is not modeled, and the load is applied on the right side, and basically you only model the left 100 millimeter of this bar. Now, the only problem is that if you're going to be only modeling the first 100 millimeter, then the load is not only downward load, but also a moment. Because if you look at the free body diagram of the 50 millimeter on the right side, way at the bottom of the page, the equilibrium requires that at the end of this very rigid bar, a moment also be acting, which is also FD. Otherwise, this will actually, move as a rigid body, and becomes it's not a static problem anymore. Okay, so this F times D, which is 1,000 times 50 millimeter, is also, as a reaction, is also applied on the extreme left 100 millimeter part of the bar. So you might say, well, okay, well, that's not a big deal, because I can apply the F here, 1,000 Newton, and I can multiply F by D, the D being the distance of the rigid section, and apply a moment there, and I solve the problem. And you're absolutely right. In fact, instead of you doing the calculation, and in this case it's very simple, we let Catia go through a systematic process to find out what is basically the moment due to that concentrated force at the right side. So basically, we are modeling only the first 100 millimeter of the bar, but subject to 2 loads: a concentrated load at the tip and a concentrated moment also at the tip. Now, so this is shown on the right-hand side at the bottom section, and the overall problem can be solve the top problem, solve the bottom problem, and do a superposition of the two. The kind of thing that you do as a superposition chapter in a strength of material course in your second year. Okay, so here is what you see there. For example, is only 100 millimeter model. This 50 millimeter is the virtual part. I've just displayed it here, but basically there's no physics into it. We are only interested in the 100 millimeter portion of the bar, and this is the deflection, and this is the von Mises stress distribution there. Okay, so let's go ahead and actually do this problem. All right, now I'm going to go to Catia, make a bar, make it square. That's what I mean. So let me make a maybe a 10 millimeter by 10 millimeter square. What is dimensions? So this is 10 millimeter. It will be 10 millimeter, and this will be 10 millimeter. I think my units are in inches, so I type 10 mm and 10 mm. Okay, exit. And because we're modeling only, because you're only modeling the 100 millimeter to the left of this bar, so I put down 100 mm. So this is the piece that is not as rigid as the piece to the right. Now, first of all, let's apply material to this. Let's take it, I don't know, maybe aluminum, metal, aluminum on this part. Okay, and let me also create a point which is 150 millimeter away from that vertical plane. So create a point. Let's see now, where was the reference elements? Get these things out. There. So it's going to be Y is 150 millimeter. This is called the handler point of the rigid visual, or the visual part, right there. Okay. Now we now go into generative structure analysis. Okay, we're doing a static analysis, so let me make this thing a little bit, the element a little bit smaller, although we can leave it like that, but that's okay. As a matter of fact, yeah, let me make it 0.2. I'm going to use linear, and then you can look at the mesh, the millimeter of this bar, right there, deactivate it. Okay, now the left side is clamped. The left side is clamped. And on the right side, I'm going to create a virtual part with this location as the handle point. So where is the virtual part? Let's see if we can find this right there. This is virtual part. And there is different varieties of these that you can make. The details you can find in that paper that I mentioned. I'm going to make a rigid virtual part. This is a rigid virtual part. You can make it more fancy by also bringing some stiffnesses, etc. And this one is called the smooth virtual part. I'll talk about this thing once I finish the problem. So virtual part, the support is this end plane, and the handler point is that location. Now, if you don't select a handler point, then it's automatically going to take the centroid of this, where these two red lines intersect. But here I would like to create a virtual handle point like that. Okay, and then I'm going to apply my load. So Where is the load? There's the load applied to this in the downward direction, direction Z, negative 1000 Newton. And of course, this is 0, and there we are. So instead of we calculate the moment and things like that, we're going to leave it like this, and Catia will automatically create the moment which due to the equilibrium of this piece that is not modeled and apply that to that end. All right, that's it. So let's go ahead and run it. Okay, and for example, let's look at the deflections. There we are, and you can animate it. So on this piece that is modeled, not only a concentrated downward force acts, also concentrated moment is acting because of the free body diagram. If you look at the deflections, there we are. I don't know whether the graphics will allow me to do the shaded one because, yeah, that's good. If I do parabolic, this doesn't come out to be good. There is a stress. Of course, this patchiness means that the mesh is not good enough, is not fine enough. But it gives you an idea of what is going on with these virtual parts. Basically, there are parts that you do not model the geometry, and you apply the load to the appropriate handler point, and automatically free body diagram of that rigid part will put the correct strain at the model part. Okay, now there was something I want to tell you about this other type of virtual part that you've got. This one, there is one which is called rigid spring virtual part, which not only it's not completely rigid. You input some stiffness as a spring element internally, of course. That its stiffness, you have to do some engineering and basically find out what the stiffness of that left out piece is. And this one is saying that it is smooth virtual part, which I didn't use. Now, when you do rigid virtual part, that square that I took at the end, you know, that support, it remains rigid. There's no dimensional changes at that. Let me hide this for a second. There is no dimensional changes at that support. However, when you do the smooth virtual part, you allow, you basically go through the whole concept, except that you allow that support to deform. Okay. Once again, if you're interested in the detail, please check this paper. I will do another video in future which deals with the dynamic effect. This was all statics.